When a modern AI agent attempts a complex task, it is immediately confronted with a massive, disorganized dataset. This includes pages of unstructured text context, exhaustive lists of available API tools, and constantly shifting environment states. All of this raw information floods into the context window at high velocity, creating a dense, chaotic environment for the model to navigate. To make sense of this, traditional agents attempt to infer latent correlations implicitly. They scan the flat text and guess at how a tool might relate to a specific subtask based on their training weights. Relying on this implicit correlation mapping over a flat text substrate is highly fragile. When reasoning requires multiple steps, these probabilistic guesses become non-deterministic, directly causing the agent to hallucinate plans or misuse tools. This failure mode is especially apparent at the frontier of agent architecture, where developers are now tightly coupling large language models with reinforcement learning frameworks to optimize for specific tasks. For these advanced RL-LLM fusions to succeed, we have to solve the primary bottleneck. Implicit relation detection simply cannot support reliable, multi-step autonomy. The architectural solution to this bottleneck is a mathematical transformation known as the structurization operator, mapping raw data, R, to a graph, G. We take unstructured raw entities, converting them into rigid teal nodes, snapping latent correlations into solid amber edges. The model no longer parses flat text. It traverses these explicit topological pathways to query exact relationships. Structurization establishes a functional taxonomy split into two operational directions, moving beyond simple static data delivery. These two halves define the new paradigm: graphs for agents, which is the forward pass of operating on a structure, and agents for graphs, the reverse pass where the agent builds the structure itself. The integration of this bidirectional loop allows for architectures that can both operate upon and dynamically generate structural topologies. Let's examine the forward pass first, starting with its most mature application, agentic planning. This structure is a task decomposition graph, or TDG. It is a strict, directed acyclic graph that maps out a primary task by breaking it down into smaller subtask nodes, connected by directional edges representing exact dependencies. In standard prompt engineering, we ask an LLM to generate steps in one shot, relying on text prediction to output a coherent plan. When we use a TDG, planning ceases to be one-shot text generation. It becomes a quantifiable decision search problem, allowing the agent to run a breadth-first search algorithm across the topology to find an optimal execution path. Because the edges formally dictate the rules of execution, decision searching mathematically guarantees that the final path respects all subtask dependencies. If the algorithm attempts an invalid sequence, it hits a missing edge and is forced to reroute. We are already seeing this architecture deployed in state-of-the-art frameworks like AgentKit, DagPlan, and LGC-Marl. By forcing the LLM's non-deterministic reasoning into strict algorithmic compliance, mapping tasks to a TDG effectively eliminates planning hallucination. This structural advantage extends beyond static task planning and applies directly to the agent's dynamic runtime environment and memory retention. These three topologies demonstrate the structurization operator applied to APIs, memory, and routing. First, tool graphs represent individual APIs as nodes and sequential compatibilities as edges, preventing the model from exhausting context on irrelevant tools. Traversing this valid toolchain topology is computationally cheaper and far more accurate than scanning a flat, exhaustive list of available tools to guess what to call next. Next is graph-organized memory. Instead of appending raw logs, the agent retains operational experience structurally. When an event is queried, a single memory node illuminates its directly connected neighbor nodes for precise relational retrieval. This targeted structural retrieval cuts through the noise and inefficiency that plagues standard semantic keyword matching over vector databases. Finally, multi-agent coordination topologies utilize fixed routing graphs to ensure messages only propagate to relevant agents, entirely avoiding the risk of catastrophic context flooding across the system. Applying structurization across execution, memory, and coordination modules provides a level of precision and computational efficiency that flat data substrates simply cannot support. But this architecture poses a critical dilemma. If an agent requires a highly structured DAG to execute a plan, how is that topological scaffolding dynamically generated in real time? This requires the reverse pass of the taxonomy, agents for graphs. This diagram shows the core mechanic of agentic synthesis. Instead of just reading a pre-built structure, the agent node ingests disorganized, unstructured text and actively outputs new topological structures. This relies on dynamic annotation and triad synthesis. The agent actively extracts text to assemble distinct subject-predicate-object triads, mapping raw data directly into strict node-edge-node relationships. Because the agent actively builds the topology, it develops immediate structural understanding, allowing it to instantly formulate and execute queries over the organized data. This dynamic in-the-loop LLM structurization is highly adaptable, replacing older, brittle information extraction pipelines that relied on hard-coded rules. Merging the forward and reverse passes reveals the complete bidirectional engine. The agent synthesizes its own scaffolding and then immediately executes a decision search over that exact same graph. This closed-loop system allows the agent and its structural scaffolding to co-evolve, providing the consistency required for complex multi-step tasks. While this bidirectional architecture is highly effective, we have to look at the current disparity in maturity between its two halves. The forward pass, graphs for agents, is a deeply mature research area, heavily benchmarked and extensively documented across planning, execution, memory, and coordination. However, this graphic illustrates the current reality. The agents for graphs reverse pass is a much thinner emerging category. Claiming the field is fully bidirectional is still somewhat aspirational. Furthermore, the structurization operator itself carries a strict mathematical constraint regarding the underlying data. If the raw data is purely independent and identically distributed, or IID, attempting to map it topologically adds computational overhead while providing zero structural advantage, resulting in isolated, useless nodes. Structurization is not a universal solution. It is a conditional architectural principle that strictly depends on the existence of exploitable relational data. Despite these constraints, the overarching trajectory of agent design is clear. We are moving away from implicit flat text processing and toward explicit, structurally queryable networks. For machine learning practitioners, the objective now is to build systems capable of sustaining this bidirectional loop. Systems capable of both synthesis and algorithmic search demonstrate a measurable increase in precision by isolating valid relational pathways from raw data noise. Stop asking agents to guess at implicit correlations. Build the structurization operator, map the dependencies explicitly, and let the agent search the graph.